So welcome back, and we're in video 3.2 of CS 1401, Recomposition. So when we've decomposed a problem into its subparts in order to make the problem easier to solve, we then have to combine the subparts back together to solve the whole problem. When we were looking at decomposition, our last example was that of putting together payroll and calculating the amount for each person in the payroll. And let's take a look at that again in terms of how to recompose. So for instance, let's look at over on the left-hand lower side of our chart, box labeled 1110, calculate gross pay. Now that's been decomposed into two boxes, into two subproblems, calculate regular pay and calculate overtime pay. And let's think a little bit about how we would combine, how we recompose those problems into the problem of calculate gross pay. And luckily in this case, it's pretty easy, right? Because your gross pay is going to be equal to your regular pay plus your overtime pay. So to recompose calculate regular pay and calculate overtime pay, we add up the results of calculate regular pay and calculate overtime pay, and that's going to be the result of calculate gross pay. So that's just a small example of how to recompose. Now, when we decompose by defining subproblems, in computing, that's typically done, at least in Java, as defining subproblems as methods. And another term for method in computing in general is function, but we can think of a method or a function as something we're going to do. So, for instance, if I want to determine this level of exercise I should do, well, then I probably, given what I know about body mass index and so forth from our last couple lectures, what I might want to do is calculate my body mass index, and then having done that, determine the goal I should have for body mass index. Now, how would I calculate my body mass index? Well, I want to get my height and get my weight. We can recompose that into calculating my BMI. And once I've got the BMI, then if I get my age and I get my general health, knowing my BMI, I can determine my BMI goal, and that will determine my exercise level. And here's what that looks like in terms of a decomposition as a chart. The overall problem is to determine the exercise level. The two subproblems are calculate BMI and determine BMI goal. And I can break down, I can decompose calculate BMI into get height and get weight, and determine BMI goal into get age and get health. And then in terms of recomposition, once I have the height and the weight, I can apply the BMI formula that we've used before. And I can, with another algorithm based on my age and my health, get a goal for my BMI, and then that will be I can use that to determine my exercise level. So if we look at this, the information contained in our decomposition chart, in terms of pseudocode, let's take our top level task is to determine an exercise level, and I'm going to use my body mass index and my body mass goal as the inputs to that, and the result of that we'll put in a variable called exercise level. Well, we can break that down though, because we know that how to calculate BMI, and based on our chart also we had a way of figuring out my BMI goal. So what we're going to do is have BMI be based on calculating BMI based on height and weight. My BMI goal will be another algorithm called determine BMI goal based on my age and health. And then I can put those two together using an algorithm called determine exercise level based on these intermediate results from BMI and BMI goal. Now, interestingly enough, I can decompose this algorithm in the same way with sub-goals or sub-tasks of determining exercise level based on calculating BMI and determining BMI goal, but I can do it without having to have separate variables for BMI goal and exercise level. How? Because I can just have as the arguments to determine exercise level the result of calculating BMI and the result of calculating BMI goal, and here's how I can combine that. These processes of decomposition and recomposition form part of a larger process cycle. That process cycle starts with the concept of abstraction, which we've looked at before. That is, simplifying the problem by getting rid of unnecessary details. Once we have an abstraction for the process, then we go into the phase of automation, and that includes the two processes we've just looked at, namely decomposition and recomposition. And once we've done that, then we can go into analysis. That is, we look at the results of our automation and its implementation, and based on that, we can go back and perhaps refine our abstraction, refine our automation, analyze again, and continue until we have a solution that we like. So the problem of recomposition helps us understand how to do a better job in the decomposition as we go through these cycles, these big cycles. It's easier and clearer to recompose program parts when the decomposition makes the transfer of information between the parts as simple as possible. That's called minimizing the coupling. When it keeps similar functions together inside parts, that's called maximizing cohesion, and hides information not relevant to higher levels of abstraction. So as we go through this cycle of abstraction and automation with decomposition and recomposition and analysis, we should be able to increasingly minimize the coupling, that is, make the transfer of information between the parts as simple as possible, maximize cohesion, that is, keep similar functions together inside parts, and hide information not relevant to higher levels of abstraction, that is, make our abstraction as useful and as simple as possible. So that's it for decomposition and recomposition, and in our next class, we're going to start thinking about how to implement these algorithms, and to do that, we're going to look at programming languages and programming environments. See you next time.